Hello, welcome to my channel. My name is Fran and today we will discuss the notion of time travel in quantum mechanics. I hope I will do it justice as the topic is complex and mind-boggling, but I promise to keep it as simple as possible. The only thing that I ask of you is that you listen with an open mind. What you will hear will challenge your common sense and your current view of reality, unless you're a quantum physicist, in which case, why on earth are you listening to this? In any case, let's start from the concept of time in classical physics and up until relativity. Before relativity, time was thought to be absolute. Einstein proved with his theory that time and space are both relative, that they are different for different observers in different frames of reference. Now, this doesn't mean that they are perceived to be different, but that they are actually different. For instance, time moves slower the faster the observer moves. And it also moves slower, closer to Earth, while it moves faster in space, away from mass. At the speed of light, time is frozen. Another feature of time in classical physics is one-directionality. In other words, it moves from past to future. This is what scientists call the arrow of time. And this is why we can remember the past, but cannot remember the future. The arrow of time is determined by entropy. Entropy is a measure of chaos or disorder in a system. In classical physics, disorder has been found to always increase in a closed system. This is due to how probabilities are calculated. There are simply many more cases of disordered states than ordered ones. In fact, the second law of thermodynamics states that entropy always increases in a closed system. This is quite obvious in cosmology. Just after the Big Bang, the universe was very smooth and pretty uniform. Then it gradually grew into a more disordered and diversified system, giving birth to planets, galaxies, and so forth. This growing complexity is what we call time. In other words, it's a measure of the evolution from the simple to the complex. Now, the reality is that it's not entirely true that entropy always increases. It's just that it's incredibly unlikely that it will decrease within an individual's lifetime. The odds are unbelievably low that any system will go from disordered to ordered. Now, stay with me. I'll give you an example. Is it easier to start from a new stack of playing cards where all the suits and numbers are in order and shuffle them into a disordered state, or is it easier to start from a shuffled stack of cards and end up by chance with all suits and numbers in perfect order? The answer is obviously the former, simply because there is only one state in which the cards are ordered and many in which they can be disordered. Therefore, in principle, it is not impossible for entropy or disorder to decrease. It's just incredibly unlikely. In nuclear physics, particles decay at different rates, and the rate of decay cannot be predicted. It's a game of probabilities. Therefore, in nuclear reactors, a huge amount of subatomic particles are employed in order to shorten the time of decay and stack the odds in our favor and enable nuclear fission. All you need is for one particle to decay to give rise to a chain reaction. In quantum physics, everything is about probabilities, but they are not classical probabilities, which can be calculated with any accuracy. They are virtual possibilities, which can be altered by observation. This was proved beyond a shadow of a doubt by the famous Young's double slit experiment. Let's see if I can summarize it. The aim of the experiment was to find out the true nature of light. Before Einstein, light was thought to be or to act like a wave, but the photoelectric effect showed unequivocally that light behaved as a string of particles, as photons of a certain frequency could displace an electron from a metal bar. So which was it, particle or wave? In Young's experiment, there were two screens, one in front of the other. The first screen had two open slits or gaps in it, while the one behind it was just a regular screen. Young and colleagues then shone a beam of light through the first screen and expected to see two bright lines on the back screen in correspondence with the two slits. However, what they did find was an interference pattern made up of alternate dark and bright lines all over the screen. The interference pattern is usually observed in wave physics, as the waves reinforce each other with the troughs and crests meet what is called constructive interference and cancel each other out when they are out of phase with one another. And this is referred to as disruptive interference. Therefore, the bright lines correspond to the constructive interference, while the dark lines correspond to the disruptive interference. This was inconsistent with the particle nature of light described by Einstein. So Young and colleagues then reasoned that the photons might interfere with one another as they hit the slits or the side of the slits, and might therefore give the illusion of a wave. So they decided to shoot one photon at a time. Now, a photon is a particle of light, so it can only ever behave like a particle, right? Wrong. The interference pattern was still present. Okay, so this was really confusing. It looked as if the photon was going through both slits at once and interfered with itself. Young and colleagues then got smarter. They placed a sensor by the slits in order to check which slit the particles were really going through. At this point, the interference pattern disappeared, and all you had on the back screen was two bright lines in correspondence with the slits. Now take a second or two to digest this information. It's as if the particles were aware of being observed and resumed acting like classical objects. They were found to go through each slit with a 50-50 chance, or with 50% probability at random. Observation seemed to have collapsed the wave into an observable particle. This brings us to Heisenberg uncertainty principle, which states that the more precisely you try to measure the position of a particle, the less you will be able to know about its momentum or motion or speed. In other words, by observing a specific property of a quantum state, you bring that property to life and make the other property fuzzier or less real in our 3D classical world. Now, in case you wonder, this experiment has been replicated many times since, and its findings have always been confirmed, even using different subatomic particles such as electrons, protons, and even whole atoms have been found to be in a superposition of states or in two places at once. The conclusion seems to be that reality doesn't really exist in a definite state until observed. But this surely can't be it, or can it? So the famous physicist John Archibald Wheeler designed a more ingenious version of the experiment by delaying the choice of whether to install the observer or the sensor until after the particle had gone through the slit in order to catch it in the act. In other words, Wheeler was trying to outsmart the wavicle or wave/particle by delaying his observation until after the wavicle had decided which slit to go through, which path to take. Well, the results were shocking. It turned out that even when the quantum observer or the sensor was inserted after the outcome of the experiment should have been decided, the act of observation still collapsed the wave into a particle. In other words, as if the wavicle, wave/particle, had traveled backwards in time and changed its behavior according to whether it had been subsequently observed or not. Now, physicists then try to outsmart the photons by linking the photons in a particular way and then splitting them up and then only measuring one of them. Now, when quantum particles are linked and split in this way, they remain entangled. So by measuring one, you can automatically establish the state of the other without actually measuring the second one. Now, the results showed that the interference pattern was erased for both photons once one of them was measured. The entangled particles were communicating instantaneously across space. Measuring one would automatically collapse the state of the other. At this point, the quantum physicist got really stubborn, as he was determined to fool the quantum wavicle. A group of physicists then designed a modified version of Wheeler's quantum delayed choice experiment. They called it the delayed choice quantum eraser. In this experiment, they observed the entangled particles go through either slit and then reunited them before they arrived at the final sensor, so that the information about the measurement would be erased and there would be no way for the last sensor to know which path the particle had taken. In this case, the interference pattern was re-established at the final screen, even though the particle had been previously observed to go through a specific slit. In other words, the act of erasing the information about the measurement would affect the path that the particle had taken backwards in time. Basically, you could rewrite the past. Cause and effect were thus reversed, and the arrow of time was found to go in both directions at the quantum level. But you might argue, this is not what we observe in our everyday life. Now, how can we interpret this information? The scientific world has been at war ever since over how to interpret these findings. First, they try to explain this by saying that quantum weirdness only applies to the microscopic world and doesn't apply to our macroscopic reality, in which classical physics still reigns supreme. Now, the problem with this interpretation is that we're made up of microscopic quantum stuff. Moreover, where do we draw the line? Where does the microscopic world cease to be micro and becomes macro? Then they tried to say that measurement at the quantum level wasn't the same as observation by a conscious mind, and therefore none of this applies in our classical space-time reality. But again, no evidence backs this up. What makes observation in the microscopic world different from observation at the quantum level? Or observation at the macroscopic world different from observation at the quantum or microscopic level? The physicist Hugh Everett maintained that observation doesn't collapse the wave into a particle, rather it splits the universe in two, creating an alternative reality, one with a wave and one with a particle. So every time an observation takes place, a new universe is created. Finally, some maintained that these quantum entities are virtual particles which represent a wave function of probabilities. The alternative realities are but virtual possibilities until observed. In other words, they all exist, but we can only ever be aware of one of them, the one that we choose to observe. To paraphrase Einstein, it appears that this space-time reality is but a stubborn illusion. It appears, therefore, that our observation doesn't merely measure existing reality, rather, it creates the reality that it observes. In other words, observation or consciousness is found to be fundamental. It comes first, whilst reality is a byproduct of it. So this is it for today. I hope I haven't completely fried your brain. And if you found this content informative or interesting, you might want to subscribe, like, or hit the bell option so more people can become aware of this reality and so that you can be notified of my future videos. In any case, thank you for listening. Have a wonderful awakened day.